In the last video, we found the volume of that yellow region when it was revolved around the y-axis. We're going to take that same yellow region bounded by y equals x cubed, y equals 8, and x equals 0. But this time we're going to revolve it around the x-axis instead of the y-axis. How's that going to look? So on this one we got that kind of bowl shape. If we take that same shape and we revolve it around the x-axis, it's going to be a different sort of volume, isn't it? Let's take a look at how that's going to play out. We'll start off again with the same shape, right? I think maybe I'll just draw that bit of it. And we'll have the x cubed part, y equals x cubed. We'll have the, that's not very horizontal. Let's try that again. That's better. Y equals 8, so again, the point 2 comma 8. And then this is still our third boundary, right? X equals 0. So the region that we're revolving is still this shape right here, but this time our axis of revolution is y equals 0, or the x-axis. Our axis of revolution doesn't actually form one of the boundaries of the shape that we're revolving. That's pretty significant. All right, so as we revolve this around, we would have like a reflection of this shape that will look something like this down here in the bottom. And we'd have these big disks, right, that are actually always going to have a radius of 8. So we're actually going to get a cylinder, right, because the radius doesn't change, right? So this is going to stay the same. The cross-section is going to be a circle of radius 8 throughout. But hold on a second. There's going to be this cavity inside of our cylinder, this gap of antimatter. We don't actually have all of that cylinder filled in. So we can talk about finding the volume of that cylinder and then subtracting out the volume that we don't want, right? So we actually have two integrals going on here. One integral from, oh, wait a second, these are still, or these are once again, rather, with respect to x, aren't they? So that radius, the radius of the cylinder, is constant. It's a constant of 8. We'll square the radius. But since we're now, our cross sections are perpendicular to the x-axis, we're going to go from not 0 to 8 anymore. We're going to go from 0 to 2, right? That's the 2 that we wanted to stop at, x equals 2, starting at x equals 0. And that's going to give us the volume of the cylinder. We don't need calculus to find this, right? We can just use pi r squared h to find the volume of that cylinder. But we have to subtract. We have to subtract the hole, right? The gap, that cavity that's inside the cylinder. We're still going from 0 to 2, but this time the radius changes, right? So I'll call this big R of x. That's the big radius. That's just a constant of 8. But this little r, that little r of x, isn't a constant of anything because it changes, right? This is the top minus bottom, but the top is changing as x changes because it's following this blue curve of x cubed. So top is x cubed, bottom is 0, so little r is x cubed. So this integral represents, oh, what did I forget? I forgot to square the radius. This integral over here, the second integral, represents the area, the volume, excuse me, of the region that we want to throw away. That's why we're subtracting it. Now, we can find these separately, or we can think about, well, the pi is in both of them. They're both going from 0 to 2, and the dx is in both of them. So the only thing that's changing here is our radius. We have a big radius, we have a small radius, but they're both being squared. So we square the two radii, we subtract them, and then we've got ourselves our volume. Okay, so we've got pi, we've got 64 integrated as 64x, x to the 6th integrated as x to the 7th, divided by 7. We'll evaluate that at 0 and 2 and subtract the 2. So we've got 64 times 2 minus 1 over 7 times 2 to the 7th. And then we're going to subtract 0, right? In this case, as in many cases, when one of our bounds is 0, then the antiderivative equals 0 when you evaluate it at 0. So let's see, 64 is 2 to the 6th. So this is actually 2 to the 6th times 2, which is 2 to the 7th. We've got another 2 to the 7th here, so I'm going to factor out that 2 to the 7th along with the pi. The only thing that's left inside here is 1 minus 1/7. That's a lot easier to deal with. So 2 to the 7th, or 128 pi, times 6 over 7. And I don't really feel like multiplying 6 times 128. I'm just going to leave this like this. If you feel like multiplying out 6 times 128, that's fine as well. So this is a new method. It's still disks, but it's the disk that we want and then the disk that we don't want. We've got disks that have disk holes in them. We call these washers, right? They resemble a washer, like with the nuts and the bolts, right? You can imagine a plastic washer or a metal washer that you have to screw a screw through, like in the middle. So anyway, this idea here is we have to find the area of the big circle, we have to find the area of the small circle, and then we subtract the two. So notice that this is exactly what we just did. We had a big radius that we squared, we had a small radius that we squared, and then we subtracted those two. And that's exactly what we did right here. The big radius was 8, the small radius was x cubed. We squared them separately. After we squared them, we subtracted, we integrated, and then we just went on with our merry business. So the washer method is really the same as the disk method. It's just doing the disk method twice. Once with the volume that we want, that includes the stuff that we don't want, and then we take away the stuff that we don't want. So the perpendicular method is really the perpendicular method again. We're just doing it twice. Has this as our formula. So we can try another example with this, can't we? This time, let's throw some trig in the mix. It wouldn't be calculus unless we switched it to trig every so often. So first quadrant, let's just worry about the first quadrant. It tells us the region in the first quadrant bounded by the y-axis, the graph of y equals cosine of x. Well, that starts at the maximum and goes down to 0 at pi over 2. This is y equals cosine of x. This is 1. And then the sine of x, that starts at 0 and goes up to a maximum at pi over 2. That's y equals sine of x. And so they intersect a bunch of times, but in the first quadrant enclosed by those two curves and the y-axis, we're talking about just this little region at the very beginning. So this region right here. And one thing we're going to want to know, probably, is this point of intersection. When does sine of x equal cosine of x? Well, when x equals pi over 4, right? Think about the unit circle. This is pi over 4 comma root 2 over 2. Sine and the cosine of pi over 4 both equal root 2 over 2. So that's oftentimes a useful thing to find, is that point of intersection. And the other thing we need to mark on this diagram is which direction we are revolving. We are revolving at about the x-axis, so we're still dealing with perpendicular cross sections. So we've got this is our axis of revolution. Draw that axis of revolution, label it as your AOR, your axis of revolution, because every single radius, every single time, whether it's the big radius or the small radius, all radii are going to be measured from that axis of revolution. That's a pretty important thing. So to find the big radius, we start at our axis of revolution and we keep on going until we get to the very edge of our shape. So this would be our big radius. Remember that this little bitty rectangle has a width of dx, and its height, this big R, as a function of x, is top minus bottom. The top is the blue curve, cosine of x. The bottom is the x-axis, which is y equals 0. So y equals cosine of x minus y equals 0. Our little r value our little r value is going to start at the axis of revolution because all radii start at the axis of revolution, but this one's going to stop as soon as we get to the shaded region, right? We don't want all of it. We just want the part we have to throw away. That width is also dx, but this time we've got a little r. Little r of x equals, well, top minus bottom. The top is sine of x, the bottom is 0, so sine of x minus 0. All right, cool. So now we've got our big R, we've got our little r, we can plug them in and we can evaluate this. So we've got the volume equals pi times, well, we're going from an x value of 0 to an x value of pi over 4. And we've got our big R squared is cosine squared of x minus our little r squared is sine squared of x. And we might start breaking out into a cold sweat because we don't really know how to integrate cosine squared of x or sine squared of x yet. We'll get there in the next chapter, but for now we don't know how to deal with those. So how do we deal with these if we don't know how to deal with these? One option is punch it into a calculator. But if we're not allowed a calculator, then we have to think of other things. Well, you might recall from pre-calculus that this is a trig identity. This is the double angle identity for the cosine. This is the cosine of 2x. This is one form of the double angle identity for cosine. Well, that's a much easier thing to integrate. So we can go ahead and integrate cosine of 2x, and that's, as long as we remember the inverse chain rule here, which we would never forget the chain rule. We're going to divide by 2 because that's the anti-chain rule. Cosine integrates to sine. The argument of 2x never changes. And then we'll evaluate that at pi over 4 and at 0. So our constant of pi over 2, and then we'll evaluate sine of 2x is 2 times pi over 4 is pi over 2, minus sine of 2x where x is 0. Well, sine of pi over 2 is 1, sine of 0 is 0, so our answer is pi over 2. This isn't a calculator problem. That's all we needed. Most important thing to remember about the washer method is this thing in bold down here. Okay? We know we're going to find two radii, the big radius and the small radius. Each one of those radii will be measured from the axis of rotation itself. That's huge. Okay? This is a very important thing. Make sure you're always drawing your radius from the axis of revolution, just like I did here, right? Big R and little r both went all the way down to the x-axis. One very common mistake that people will make is they'll say, oh, this is little r right here from the top to the bottom, right? Because that's the region that we care about. No, because the top curve and the bottom curve, neither one of these is the thing we're revolving around. This purple thing right here that is true is not a radius. If you wanted to find the area of the yellow shaded region, sure, yeah, we would want this. But no, don't find that purple distance in this particular case. That's a big mistake. Another big mistake is that people will subtract these two and then square it. No, we're finding the area of the two circles separately. So pi big R squared minus pi little r squared. So the only thing that order matters, right? We have to make sure we square before we subtract. So you're going to factor out the pi, you're going to factor out the dx, but we still have r squared minus r squared. Important, r squared minus r squared is not the same thing as r minus r squared. We know that these aren't the same thing, but people will constantly do this incorrectly to get that wrong answer. So just draw yourself a picture, always draw your radius to the axis of revolution, and everything should be hunky-dory.